All right. So the first topic we are interested is in topic of counting. Yeah. Why do we count? Well, I mean, we want to understand how many of some types of objects exist, right? For whatever reason. Right? So this is the first topic we are interested in. So counting. All right. So uh, what we need is some methods on how to count properly. Okay, because if the object we are trying to count is complicated, then we don't want to double count or over count. Okay, so we want to have a system for how to count things. Let's see. Uh, so what is the counting? Counting is a method used to compute the number of elements in a discrete event, right? I mean, like if an event is continuous, then there are infinitely many elements in it. You don't care about counting in that case. Yeah, you only care about counting when the event is discrete. Sometimes we also are interested in counting the event which is not discrete, but that is a special case, right? So for example, I can give you an example. Suppose I give you a square, yeah, and I draw a circle inside it. Then I'm asking if the drop is falling. I'm asking what is the probability that raindrop will fall inside the circle. Okay. But again, that's not our concern here. Our concern here is basically what our concern here too is to count discrete objects. Discrete means there's a gap. Okay. So now what are the applications? Well, as we already talked about probability, right? So probability is the one major application of counting. And then analysis of algorithms. Okay. In computer science, in particularly in complexity theory, it is the important problem to say, hey, how fast or how slow an algorithm is. There's a concept of running time of the algorithm. How much time does an algorithm takes to run, right? I mean, that's how, say, for example, if you have started doing any computing yet, you would have already seen different kind of sorting, right? Bubble sort, heap sort, so on and so forth, right? So those algorithms are designed, basically, those algorithms are basically thought about based on how much time it takes to run, all right, based on the size of the input. So these are the two important reasons why we should study uh, counting beyond the other numerous ones. So now let's look at few examples of counting, and we will at the end be able to solve these problems with ease. How many different license plates are there with 2 letters followed by 3 numbers? Right? What are all the possible? So how many such license plates are there? Another interesting thing would be how many ways can you select 3 books from collection of 5 books? 15 books, my bad. Yeah, or 5 books, doesn't matter. Yeah. So these are the few counting problems. Yeah, and they have application, right? Like say, for example, IP4 versus IP6, right? I mean, like now we moved to IP version 6 because, well, we said, oh, okay, IP4 is now like, IP4 is more like, is not long enough, right? Or another example is suppose you went to a party and somebody gave you a number and you're missing 1 digit, say last 1 digit, or say you're missing last 2 digits, or you're missing last 3 digits, right? If you're missing last 1 digit, then you may try to call the person. But if you're missing last 4 digits, then you will not attempt to basically, try to see all the combination to find that person, right? I mean, so basically these are some, and you can basically have an idea. Oh, if the 4 digits are missing, then how many combinations do I need to call, right? Or for example, somebody left a briefcase in your house and you want to open that briefcase for whatever reason. If it is like 4 digits, if there are 4 digits in them, then you may try to do it. But if there is, say, suppose 16 digits, then you may say, okay, it's not possible within this given point of time. So these counting problems are important. They give us an idea about how much time a particular task will take. Yeah. Similarly, for example, another example is they will take an iPhone, for example, right? I mean, suppose the iPhone has 4 spots, like, the passcode has four spaces in it, right? And suppose those are numbers. Yeah. You can basically decide what is the security of your iPhone. Yeah. Suppose you can say, okay, after every wrong attempt, it basically increases by 2 minutes or 5 minutes. You can do an exact analysis, not exact in the sense of average case analysis of how much time it will take for somebody to break the iPhone by the usual method, right? So these are the few applications. This helps us actually to understand, gives us an idea about how things work out. Okay. So let's see. So let's start with a warm-up example. So on Friday night, I have a choice of several activities. So there are group activities and individual activities. So group activities, movies are Thor, Hannah, Fast Five, Limitless, and say board game is Monopoly, Trivial Pursuit, and individual activities are say reading a book on discrete math, C++, Java, or playing video games. Yeah. All right. So now the question is, if one chooses one group activity, how many choices they have? Yeah, 6, right? Do you agree? So you are saying, oh, well, I mean, how are you basically just, so you are essentially just saying, okay, let me add this up. So I have 4 plus 2. So essentially I have what? 4 plus 2, which is 6 ways. Or 6 choices, really. Yeah. So you did not say 4 times 2. You basically added all the events and said, okay, you added all the possibilities here. You had 4 plus 2, which is 6. Yeah. So you have 6 choices here, right? We want to basically make the idea clear here, why we have only 6, okay? So now, let's look at another example. If someone wants to go for a movie, then a board game, how many choices do they have? So how many movies are there? 4. And there are how many board games? 2. So if you say you went to watch Thor, then you have what? 2 options for the board game, right? If you saw Hannah, you have what? 2 options for the board game as well. So similarly for the other 2 movies as well. Yeah. So in this case, you have how many options? Then you have 4 times 2, which is 8 ways. Okay. Yeah. So in this case, we have 4 times 2. Yes. Whereas here we had what? We had 6 ways. Yeah. So what is the fundamental difference between these two counting? All right. So, sorry. Yeah. So why is that rule applicable? So let's try to formalize this. So the first one is the rule of sum. Suppose you have basically, the rule of sum applies in the following scenario. Suppose you have 2 tasks. Yeah. The tasks are, first task can be performed in m ways and second task can be performed in n ways. And 2 tasks are mutually exclusive. You do this doesn't mean anything about this task. Okay. Then performing either of tasks can be accomplished in one of m plus n ways. Yeah. So if you go back here, how many activities to choose on Friday? Yeah. You have one task is to watch movie. Other task would be to play the board game, right? And you can do any one of these tasks and you don't care. They are exclusive. They don't interact with each other at all. Yeah. So therefore we have what? How many ways to do this? We have 4 plus 2. So therefore in this case we have what? 4 plus 2. Yeah. I don't even want to write them as 6. Yeah. Because when I write 4 plus 2, it becomes much more, okay. This is what is happening. Okay. So similarly, we have the other rule, the rule of product. So rule of product is if you have a task which can be broken into 2 parts, say for example, yeah. And the rule of product is if you have a task which can be broken into 2 stages or 2 parts, the first one has m possible outcomes, second one has n possible outcomes, then the whole task can be accomplished in how many ways? M times n ways. So for example, so BC license plate consists of 3 letters followed by 3 numbers. How many license plates are possible? So let's try to investigate this. Okay. So now I have a task. We have a task of basically designing what? We have a task of designing 6 So 3-letter word followed by 3 numbers. So we have task of finding this 6-length string, and we can break it into what? We can break it into steps. Okay. So what steps can we break it into? We can break it into 6 stages actually. Instead of 2, we can break it into 6 stages. So let's say 1, 2, 3, 4, 5, 6. Okay. All right. Now the first one can be done in how many ways? So 6 what? Letters, right? So how many letters are there in English? English there's 26. Yeah. So English there's 26. So the first one can be filled in 26 ways. Do you agree? The first task of finding the first letter. Yeah. The second task of finding the second letter can be also done in what? 26 ways. Right? Because, well, I mean, there is no problem in repeating. There's nothing said about repeating or not repeating it. Similarly, the third one can also be done in 26. So this is how we found out what? The letters. Now let's go back to the numbers. So how many numbers are there? So again, we are assuming, we are using English and the decimal numbers, right? So there are how many decimal numbers? So 0 to 9. So there are 10. So 10 for the first, 10 for the second, 10 for the third, right? So the total number of ways is what? So therefore, 26 times 26 times 26 times 10 times 10 times 10. Does it make sense to you? Yeah. Why is it multiplication? Because you had this big task, you broke it into stages, and basically the idea is that so first can be done in some many ways, and then you go to the second one, and so on and so forth. Okay. So then the answer here is simply is 26 to the power 3 times 10 to the power 3. So these many license plates are license plates are possible. Yeah, does it make sense? Okay. So this is so-called application of rule of product. Okay. Let's move on and look at a few more problems. Now, let's so next step is to basically talk about permutation. So let's look at the following. So what is an anagram? Anagram is basically a game where we take an English word and rearrange the letter and arrive to other English words. Okay. So this is slightly ambiguous. I'll tell you why. So we'll write down all the possible anagram of art. So basically, we are just rearranging the words. Okay. So what do we have? So art. So one is art itself. Then we can have what? Tar. Okay. So let's do slightly systematically. So what do you think? What should we do? We can have ART. Then we can have ATR. Yeah. Then we can, let's say, then the next one would be, say, let's take R. So we have RAT and we have RTA, right? And then the next one, then the next possibility is what? TAR and TRA. Yeah, all right. Yeah, I'm trying to do it in a systematic way, because if you try to approach systematically, then we are able to write down all the possibilities easily. Otherwise, we'll have to keep guessing. Oh, is it there or not? Is it there or not? Okay. So these are all the anagrams of art. Okay. So there's a slight ambiguity in this statement because, well, I mean, we are saying all the English words. Yeah. So these are English. They cannot be really thought of as an English word because, so by word here, we mean basically collection of what? Collection of letters. Yeah. We don't care if there is a meaning or not, right? Okay. Makes sense. So these are all the anagrams. Does this make sense to you? Yeah. Okay. Let's move on to the next problem. How many different ways are there to rearrange the letter in the word art? So let's see how we come to that conclusion. Okay? So again, we have art. So there are 3 spots, isn't it? So we have first spot. We have first spot, we have second spot, we have third spot. All right. And how many letters do we have? We have 3 letters. A, R, and T. Right? Now, the first spot can be filled in how many ways? 3 ways. So the first spot can be filled in 3 ways. Right? So again, you should think about it from the rule of product perspective. We have this idea of having a 3-letter word. We are breaking this problem into 3-stage problem. Okay. Even I don't want to think it like this. This problem is so stupidly trivial that I don't want to think it like that. The idea is you still have to think it in that way because, you know, it's like machine learning. Machine learning, you train on data you already know, and then you try to do problems which are harder. So this is what we are doing as well here. We are trying to train on simpler problems so that we can approach slightly harder problems. All right. So here, so let's go to this. So how many different ways are there to rearrange the letter in word art? So again, as we said, the first, so we are breaking it into 3 steps. First one can be filled in any of these 3. So we have 3 ways. But once that guy is decided, for the second one, we have how many ways? 2. And then we have what? 1. So the answer is basically 6. Yeah, does this problem make sense to you? All right. So we are moving somewhere. Now, let's take this problem. There are 25 students in this class. Actually, there is exactly 25 students in this class. It's kind of a coincidence. The top 5 students will receive A. How many such arrangements are possible? Okay. So we again have how many spots? We have 1, 2, 3, 4, 5. Right? So 5 spots, right? So first one can be filled in how many ways? 25. Second one, 24, 23, 22, and then 21. Right? So these are the ways we can fill in. So it's going to be 25 times 24 times 23 times 22 times 21. Okay. Now, question here is there an ordering in this? Yeah. So there seems to be an ordering here, right? So we will basically try to come back to it. So yeah, so this one has an ordering associated with it. Oh, this guy got an A, this guy got an A, then this guy got an A, then this guy got an A. Generally, when you assign grades, the ordering does not really matter. Do you agree? Right? I mean, like if you have A, then you have A. You know, 10 of you have A, then you have A. It doesn't matter which one, who was assigned grade A first. So we'll come to this subtle point when we're talking about combinations. Okay. So just let's leave a remark for ourselves. Does the ordering matter? Yeah. So we will leave this question and come back to it soon. Okay. Now, so you see 6 ways. You have 3 times 2 times 1. So sometimes such a thing can be better represented by a following symbol called 3 factorial. All right. So we need factorial notation. Yeah, why? Because it's the ease of expressing your solution. All right. So what is the factorial notation? So factorial is defined only for non-negative integer. All right. So how is it defined? It is defined as follows. 0 factorial is given to be 1. Yeah, that is the definition basically. That is the definition which is kind of given so that it fits with the bigger theory. And n factorial is simply, so for example, 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Yeah. Similarly, n factorial is going to be n times n minus 1 times n minus 2 all the way to 1. Okay. The generalization of factorial function, we don't care about it, but they are called gamma function. You can look it up if you are interested. But in our course, we are interested in factorial. So far, good. All right. So this comes, here comes our first interesting definition in some sense. If there are n distinct objects and R is an integer, the number of permutations of size R for these n objects is P and R, which is given by n into n minus 1 into n minus 2 dot 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 n minus 1 R plus 1, which is same as n factorial divided by n minus R factorial. Okay. I want to come back to this definition because, I mean, just this definition on its own has no real power in it. Let me first do this problem and then we can come back to it. If I say here the order matters, then, because say suppose there are 5 students, A, B, C, D. Yeah. So then you have A, B, C, D, E will be counted differently as B, A, C, D, E. Yeah. They are counted separately. Yeah. But as I said, I mean, but when you have 5 people and they get same grades, the order does not matter, right? So in that sense, if the order matters, then this is a solution already here, right? If the order matters, then yes, I could have written this as now 25 times 24 times 23 times 22 times 21, and I will multiply top and bottom by 20 factorial. Yeah, this is a trick to complete the factorial, right? Isn't it? Because I have 21, then I need to, if I want to write it as 25 factorial, I have to go 25 times 24 times 23 times 22 times 21 times 20, 19, 18, blah, 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 multiply all of them, right? So sometimes you want to write it in a compact form. So what you do is you complete the factorial. So you multiply top and bottom by 20 factorial. So the top becomes what? So the top becomes here. So top here is 25 factorial. And the bottom is what? 20 factorial, which is same as 25 minus 5. Yeah. So this is a compact way of writing. Yes.
So can we say that R is on 5 in this case?
Yes. In this case, R is 5. Yeah. But again, as I said, if the order matters, then this is a solution. Yeah. If the order does not matter, then this is not a solution. Okay. So, right. So this would be an interesting problem. So how many permutations of letter, how many permutations of letters of word length? Okay. So let's see how do we basically write this down. So now we are doing permutation, right? Yeah. What is n in this case? 1, 2, 3, 4, 5, 6. So n is 6. What is my R in this case? What length I'm taking? Here it says what? Doesn't say any length. So we're taking length to be what also? 6. So this is also 6. Yeah. So then all the permutations of this is going to be P 6 comma which is going to be what? 6 factorial divided by 6 minus 6 factorial, which is going to be 6 factorial. Does that make sense? Yeah. Or you can, instead of using the permutation formula, you can directly apply. Hey, you can say, okay, there are 6 parts here. 1, 2, 3, 4, 5. 6, right? First one can be filled in how many ways? 6. Second one, 5, then 4, then 3, then 2, then 1. Yeah. So total number of ways is what? 6 factorial. Yeah. Now, let's ask the following question. How many permutation of letter ball are there? Okay. So here it is slightly different than the previous one. Because why? Because we have two things which are same. Yeah. So let's try to write down everything again. Okay. So let me just call this as L1 and L2. Okay. The reason why I'm calling them L1 and L2 because I want to distinguish these two L's. I'm thinking about them separately for a moment. Okay. So now I have 4 objects, right? So let me just write down. Oh, what are all the 4 objects? So what are all the permutations possible? Let's say B. Then we have A, L1, L2. We have B, A, L2, L1. Yeah. Then we have what? Say, let's change it. A. Then we have what? B, L1, L2. And then we have what? A, B, L2, L1. Right? Yeah. Now let's go further. So we have L1, say B, or let's say A, okay. I'll go by your choice. A, B, L2, and then I have L2, A, B, 1. Yeah. So observe the following. For every choice, yeah, for every choice, if I don't distinguish between them, it is what? L1, L2, and L2, L1 are same. Do you agree? Yeah. So if I think about these as 4 distinct objects, then what are all the possible ways to organize these 4 distinct objects? It is 4 factorial, right? Yeah. So 4 factorial ways to organize all 4 letters, distinct letters. Do you agree? Yeah. But out of that, for every option, we are doing overcounting, right? L2, L1, L1, L2. Everything is getting counted by what? 2 times. Do you agree? So we need to come back, divide it by what? 2 to come to the exact number. So it should be what? By 2 factorial. You say, why 2 factorial? Why not just 2? Let's take an example where we will get the factorial. All right. So let's take an example here. Say, let's make some space and then we can take a break. So draw. Okay. Let's take an example with 3. So let's take a letter with 3 in it. Okay. So let's just take A, L1, L, L, L. And look at all the combinations of this guy. Easiest of all, isn't it? So we have what? A, L1, L2, L3. Then we have A, L1, L3, L2. Then we have A, L2, L1, L3. Then we have A, L2, L3, L1. Then we have A, L3, L1, L2. We have A, L3, L2, L1. Yeah, this is just one where A is in front, and then you have all the possible. So how many of these guys are there? 6 of these, right? So you can think about it in the following way. For every, and then you can do L1, A, L1, L2, L3, right? For example, and then you can write down. Yeah. So what is the best way to count instead of doing all that? You first think about all 4 of them separate. Yeah. So if all 4 of them are separate, then all the possible ways to combine them is what? 4 factorial. Do you agree? Yeah, so first one, second one, third one, fourth one. So first one can be filled in 4 ways, second 2 ways, then 1 way, right? So these are the ways you can fill in these 4 spots. Okay. Now, out of those 4, like when you fill this, out of them, some are basically repeating because L1, L2, all these are same, right? L1, L2, L3 or L2, L1, L3, L2 or L2, L1, L3. So 6 of them will repeat. In fact, these 3 L's can permute among themselves. How many different ways can I arrange 3 L's? I mean, if they're different, 3 factorial. So for every possibility, I'm counting what? 3 factorial times extra. Yeah, so I need to divide by that. So I'm going to divide it. So this is the number of ways of counting what? Letters A, L1, L2, L3. All right. Does that make sense to you? Okay. I'll do one more problem, then I'll stop. So this is the idea behind permutation when the objects are repeated. Okay. So it's a permutation without repetition though. Without repetition means we'll come to that. So suppose you have an object where there are n1 indistinguishable object of type 1. This indistinguishable means what? They cannot be differentiated. Like all these L's, right? These L's are indistinguishable. We are just naming them L1, L2, L3 to come to the formula, but the idea is that they're indistinguishable. All right. Similarly, you have NT indistinguishable object of type 2 and NR indistinguishable object of type R. And of course, they should all, when you combine all these R, NR, N1, N2, N3, N4, N5 objects, they should be all equal to N. Then the number of distinct permutation possible is N factorial divided by N1 factorial, N2 factorial, all the way to NR factorial. Okay. So this might look slightly crazy, but think about it in this way. For every, say, suppose, let's look at this letter. Okay, let's maybe work with an example. So banana, how many different permutations are possible? So let's see, how many letters are there? 1, 2, 3, 4, 5, 6, right? So 6 letters. Now let's see the repetition. How many countings of A? 1, 2, 3. So 3 A's, right? 3 A's. How many B's? 1 B. And how many N's? 2 N's. Yeah. So number of distinct permutation possible of this word would be 6 factorial, as if you're treating them differently. I'm again not relying on the formula, but I'm trying to think about it. Let's just think about all of them different. So there are 6 of them, right? Let's see. 1, 2, 3, 4, 5, 6. Yeah. So 6 of them. So they will be arranged in 6 factorial ways. Yeah. But out of that, now there is same letter A 3 times. So we have to divide by 3 factorial because those many will basically, give the same result. And how many N's? 2. So divide by 2 factorial. Yeah. And if you want to be, say, I want to be more precise, then you can also write 1 factorial. Although 1 factorial is 1. Okay. So this is the number of ways you can have permutation of word what? Banana. Is that making sense? Yeah. I mean, how many ways are there? We don't need to. This is good enough as a solution. Okay, that's it. You don't have to simplify and give me a number. We don't care. In fact, that is an ugly answer. When I look at a solution like this, it is better because it tells me the whole picture. If you give me the answers to something like say 25 or whatever, 24 or whatever, that answer is no good because it's not telling me what is happening. Make sense to you? Yeah. All right, so these 2 things we'll skip. All right.